In today's video, we'll look at a super interesting population growth model. This is a rather simple-looking differential equation. It says dy over dt equals to ky squared. That is, the derivative of the function is proportional to the function value squared. The consequence of this model is quite unsettling, to say at least, because it predicts the end of humanity, which is Friday, 13th of November next year, supposedly. So in this video, we'll first solve the differential equation without real-life context. And then we will look at its predictions versus some actual data. And we will explain the underlying mechanism, that is, under what circumstances can this model occur, and perhaps most importantly, is next year really going to be the end of humanity? Let's go. This differential equation is a separable equation, so solving it is not hard. We can use the method of separation of variables. By separating the variables, we have dy over y squared equals to k dx. We then integrate both sides. So the left-hand side, the integral of dy over y squared is minus 1 over y. And the right-hand side is kt, plus c, the constant of integration. Rearrange, and we get y equals to 1 over c minus kx. Here we abuse the notation c. The c here is really the negative of the c in the last step, but c is an arbitrary constant, so it doesn't matter. We then use the initial condition to find c. Plugging in t equals to 0, and we get y0 is 1 over c. So therefore c is 1 over y0. Therefore, y of t equals to 1 over y minus kt is the solution to the initial value problem, which we can rewrite as 1 over k over tc minus t, where tc is 1 over k times y0. Notice that when t approaches tc, yt approaches infinity, so therefore tc is the vertical asymptote of the solution. But to be a solution to the differential equation, the function must be differentiable, namely dy over dt must exist. Here, the function yt is not even continuous at tc, so this solution is only valid when t is less than tc. And here we plotted a few solutions that corresponds to different initial values. The larger the initial value, the smaller the tc. This is illustrated in the graph. So if we interpret y as the size of a population, the model tells us for any non-zero initial value, the population always blows up in finite time. Mathematically, if t is greater than tc, yt becomes negative, so the solution becomes meaningless. And for that reason, tc is a doomsday of the species predicted by the model. At this point, you might think this is ridiculous. In no way can this model be realistic. But that is not the case. In fact, this remarkably simple formula describes the world population dynamics in the last 2,000 years almost perfectly. The model we just showed is a simplified version of a model that was proposed in 1960 by the famous physicist Heinz von Foerster. The following formula describes the population dynamics remarkably well. It says nt, the population at time t, equals to 179 times 10 to the 9 over 2026.9 minus t, where t is year in Georgian calendar. In the diagram, the black dots are actual data, and the smooth curve is a graph of the function. The fitted model has an R-squared of 0.9966, which is extremely high. Roughly speaking, over 99% of population variation can be explained by this formula. Just to give an example, the actual world's population at the start of 1999 is this figure, 592,478,7816. And if we plug in 1999 into the formula, and we get 598,662,2074. This is a prediction, and it has a relative error of 1.04%. So according to this formula, the constant in the denominator, 2026.9, is the doomsday of the world. We call this kind of growth formula hyperbolic growth because the graph of the function is a hyperbola. Interestingly enough, similar predictions were made about the world GDP, also known as GWP, the gross world product. According to economist Angus Maddison, the world's GDP over time also has a simple formula with an asymptote. It says GT is a constant, which I will not read, over 2005.56 minus t squared. This formula also fits the data extremely well, with an r squared of almost 100%. This formula was published in 2001, and as we can observe from the denominator, around the middle of the year 2005 is the Doomsday for the world economy. This formula is obviously now obsolete, but it is quite a remarkable fact that over 2,000 years, both the world's population and the world's GDP evolve over time according to simple formulas. And we call the form of the formula for GT quadratic hyperbolic growth because of the square on the denominator. So the question is, can the dynamics of the world's population and GDP be explained by some kind of mechanism? And that is our next goal. Let's look at some examples of growth mechanisms. Perhaps the most famous mechanism is exponential growth. It assumes a constant growth rate. That is, the speed of growth, dn over dt, divided by n, the population size, is a constant. Or by rearranging, dn over dt is r times n. Namely, the derivative of the function is proportional to the function value itself. Mathematically, the only function that has this property is the exponential function, and that's why it's called the exponential growth. The underlying assumptions for this kind of growth include no resource limitations and stable birth and death rate. Namely, the species does not improve over time. The latter is obviously not true for humanity over the last 2,000 years. And in particular, death rate has dropped significantly. Another common growth mechanism is the logistic growth. In this situation, we assume that the environment has a carrying capacity, and that is the maximum sustainable population size. In logistic growth, the growth rate decreases linearly with respect to population size. So we have dn over dt divided by n, that is the speed over size, equal to r, a constant, times 1 minus n over k. As we can see, the right-hand side is a linear function of n. Rearranging, and we can write the differential equation for logistic growth as dn over dt equals to rn times 1 minus n over k. Because the right-hand side has a quadratic function, dn over dt has a maximum, namely when n is equal to k over 2, half of the carrying capacity. So as we can see, the population starts growing slowly, and when n reaches half k, the speed is maximized, and after that, the environment begins to saturate. So the population approaches the carrying capacity as t goes to infinity. We notice that in the differential equation, when n is small, the quadratic term is negligible, so we have dn over dt approximately equal to rn, thus recovering the exponential growth. When the population is small, it doesn't feel the carrying capacity, i.e. the limits of the environment. So exponential growth and logistic growth are examples of mechanisms. That is, differential equations accompanied with real-life interpretations. So the question is, what is the underlying mechanism or real-life interpretation for our differential equation, dn over dt equals to kn squared, namely the hyperbolic growth? The mechanism we're about to present explains the dynamics of the world's population and total GDP simultaneously, at least prior to the turn of the 21st century. We begin by stating our assumptions, which are of course by nature speculative. We will explain the reasonings of those assumptions in detail. And whenever possible, we will use actual data for validation. Our first assumption writes the world GDP as a function of the level of technology and population size. It says the world's real GDP, aka GWP, increases with respect to the level of technology. And given the level of technology, GWP increases with respect to the population size, in accordance with the law of diminishing returns. And the functional form is G equals to T times n to the alpha, where alpha is a constant parameter that is greater than 0 and less than 1. So in the formula, the factor T stands for the level of technology. And given t, g is a power function of the population size n. The exponent alpha is positive to make sure that g is an increasing function of n. But why do we want alpha to be less than 1? This is where the law of diminishing returns comes in. When alpha is between 0 and 1, g as a function of n concaves down. This way, the slope decreases as n increases. This relationship between production inputs and output is known as a production function in microeconomics. And this functional form of the production function was introduced by Cobb and Douglas. Our next assumption has to do with the growth of technology. It says that the growth rate of technology is proportional to the total population. In the form of a differential equation, we have d big T over d little t over big T. D big T over d little t is the speed of growth of technology. Divided by t, the current level of technology, gives us the growth rate. And this is equal to a times n, where a is a positive constant parameter. N, of course, is the population. We may rewrite it as d big T over dt equals to atn. That is to say, the speed of increase of technology is proportional to the product of the technological level times the population. This hypothesis was first introduced by Kuznets and later refined by Cramer. In particular, Cramer wrote the following to justify the assumption. High population spurs technological change because it increases the number of potential inventors. All else equal, each person's chance of inventing something is independent of population. Thus, in a larger population, there will be proportionally more people lucky or smart enough to come up with new ideas. And our third and final assumption is about the speed of population growth. It says that the speed of the population growth is proportional to the real GWP. In the language of differential equation, we have dn over dt equals to b times g, where b is another positive constant. The idea of this assumption is due to the Russian anthropologist Andrei Korotayev and his colleagues. And here we have a summary of the three assumptions. We're going to show that under these assumptions, n undergoes hyperbolic growth and g undergoes quadratic hyperbolic growth. But before we do that, I'll briefly comment on these assumptions. Notice that big T, the level of technology, is not an observable. And not only that, it is hard to pinpoint a period of history in which the level of technology is constant. This makes the first two assumptions difficult to verify. In contrast, the last assumption, dn over dt equals to bg, is easier to verify. Let's look at some data and see how good this assumption is. So due to limited time, I was only able to find the world's GDP and population data over consecutive years, which is really important, from 1960 to 2022. We can first calculate the population increment. That is the difference of population between consecutive years. And then we plot the population increment against the GDP. The plot on the right is for data points between 1961 to 1990. So we have 30 data points in this chart. According to the third assumption, these points should roughly lie on a straight line passing through the origin. So we fitted a straight line with zero intercept. On the plot itself, it may look like the fit is not very good. However, the r-squared for the line is 0.96. So we conclude that assumption 3 is reasonably met, at least for these 3 decades. Interestingly, the pattern breaks down quite significantly if we include more data up until 2022. R-squared drops to 0.8. So assumption 3 is not very reasonable for more recent data. In the last part of the video, as promised, I will derive the conclusion based on our 3 assumptions. We start by eliminating dt in the 2 differential equations. The derivative of n with respect to big T is equal to dn over dt divided by d big T over d little t. By the differential equations, this is equal to bg divided by atn. Next, we use the production function g equals to t times n to the alpha. So the big T's on the upstairs and downstairs cancel, and we have b over a, which is a constant, times n to the alpha minus 1. This is a separable differential equation. Separating the variables, and we have n to the power of 1 minus alpha dn equals to b over a times dt. Integrating both sides, and we get 1 over 2 minus alpha times n to the 2 minus alpha equals to b over a times t plus the integration constant c. We assume that t is equal to 0 when n is equal to 0. This is because when the total population is 0, there is no technology to speak about. Substituting n equals to t equals to 0 into the result of integration, and we have c equals to 0. Therefore, 1 over 2 minus alpha times n to the 2 minus alpha is equal to b over a times t. We write k equals to a over 2 minus alpha. The relationship between n and t now reads k times n to the 2 minus alpha equals to bt. Now we have a relationship between n and t. Let's use that to get a differential equation for n. dn over dt is equal to bg, which is equal to bt times n to the alpha. b times t is k times n to the 2 minus alpha. Substitute that in, so we have dn over dt equals to k times n to the 2 minus alpha times n to the alpha. And this gives us the differential equation that we wanted. dn over dt equals to k times n squared. And as we showed in the very beginning of this video, the solution to this differential equation is exactly hyperbolic growth. Therefore, we have n equals to 1 over c1 minus kt, where c1 is an arbitrary constant. And last but not least, let's simplify the expression for g. Since k times n to the 2 minus alpha equals to bt, t is equal to k over b times n to the 2 minus alpha. Multiply that by n to the alpha, and we get k over b times n squared. And since n is 1 over c1 minus kt, g is equal to k over b divided by c1 minus kt squared. So overall, we have hyperbolic growth for n and quadratic hyperbolic growth for g. This concludes the demonstration of the growth patterns for n and g under these three assumptions. And because, as we have seen from the data, the third assumption, dn over dt proportional to g, is no longer reasonable, the growth patterns for n and g are unlikely to continue, which in turn invalidates the Doomsday prediction that is next year. At least I hope so. Thank you very much for watching. I'll see you next time. Bye.